Good afternoon, Professor.
Good afternoon. Good afternoon, Savannah. Good afternoon, Caroline. That's awesome. Hello. And okay, I'll do the chat first. Awesome. Thank you. Good afternoon, Caitlin. Good afternoon, Amanda. Excuse me. Good afternoon, Kevin. Good afternoon, Arini. Good afternoon, Adan. Good afternoon, Evan. Good afternoon, Mackenzie. Good afternoon, Amy. Hello. And good afternoon, Jose. Good afternoon, Somaya. Awesome. Who else did I say? I said Jose. Wait. Okay, that's the chat. Sorry. Oh, good afternoon, Stephen. Thank you. Awesome. Good afternoon, Kevin, Amy. Yes, I think I've said good afternoon. Well, I'll just make sure. Okay. And good afternoon, Amanda. Well, good afternoon, Caroline, Jose, Amanda, Caitlin, Mackenzie, Savannah, Evan, Kevin, Adon, Erini, Sumaya, Stephen, Erica, Rashman. I didn't say hello to. Hello, Rashman, and hello, Amy Cardenas. Oh, that's right. The two Amy's are in two different classes this semester, but they were in the same class last semester, I think. Anyway, okay. And who was that? Good afternoon, Stephen. Right. Okay. So I had all these announcements, but I don't remember any of them. But the board, of course, the board. But it was, I do think, all right, I just lost the board, but that's because, as Douglas, who's not here right now, pointed out, it's because I wasn't using it enough right now. We're going to use it a lot today, so hopefully that's the last time that will happen today. And okay. Sorry, hold on. Oh, and Kevin is here. Hang on. Good afternoon, Rashman. Thank you. Awesome. Wait, and sorry, okay. The board is back. We're going to use the board. So here's the deal. As I say, I actually think I had. Oh, I know what it was. Do one quick announcement. And that is, again, my office hours. If there's any lack of clarity on this, the best time to find me physically in 3D is between 11 and 1 on Tuesdays in 046105. I'll put that in. Oops, sorry. I think that's in the syllabus. I think it's in Google Classroom. It should be, but just in case, when I'm doing this again, because this came up in the other class, and you don't need an appointment to do this in general, although it's always good if you're going to let me know, but hold on. Okay, and but any other time, so that's in general. That's like really is the time to find me physically. I'm not in the building or even in New York a lot other than that. But to make any kind of phone appointment or Zoom appointment or anything, you can always do that through this. I know we've said this before, but again, this came up. This is the kind of information no one ever needs until exactly they need it. And then the moment you need it, you really need it. And then, oh, sorry. Yeah, totally. Yes. Hold on. Let me say that again. A good question, Rashman. And by the way, please submit that question for extra points for participation. That is a great question. Hang on. Yes. You, as long as you either text me at that number or email me at that email address, we can make an appointment to do a Zoom. So yeah, I am. I mean, those hours that I just put up there, it doesn't really make sense for me to Zoom because I'm right there and there might be students with me in the office, but I could Zoom at other times as long as we just arrange it. Yes. And or some people prefer phone calls, and sometimes that's better. So I could do that too. But yes, but then we have to make an appointment. And can you just make it clear to me, Rosh? We would have to make an appointment to do that. But I'm happy to make an appointment to do that. So could you just tell me, Rashman, if my answer is clear or if I answered your question? I just want to make sure. All right, well, we'll see in this. Well, here. Okay. Okay. But the reason I'm saying all of this about my office hours and everything is that this week it'll be very hard to catch me in that time. If you need something like something signed or something, you could catch me right at the beginning, like right at 11 probably, but I do have to leave very early this weekend, this Tuesday. Tomorrow I won't be there for much of it, so please let's make an appointment, any of you who need anything. I have to leave early tomorrow for something in Brooklyn. Actually, my brother is becoming a lieutenant in FDNY. So, you know, that's a big deal. And we're very pleased about that. So I would, all right, anyway, all right, let's, okay. Physics. We still have, oh, thank you very much. That was such I just threw that out so unsubtly, but thank you. I totally appreciate it. But yes, I do. I'll take it. And since it's him, got it. No, thank you. I appreciate it. I'm very pleased. Very proud. Okay. Oh, and Douglas just came, and that reminds me, I better start using this board before we lose it again. Okay. So here's what we're doing today. I just hit it. Oh my God. And just when Douglas is coming in, that's so embarrassing. No, I just touched the board. I promise. Wait. Okay, wait, here it is back. Okay. 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 Here's what we're going to do. So we're still in the middle of homework 1 again. And I put a note in the Google Classroom, like there's nothing new due for a while. We're on homework 1 for a while. If you've already turned it in and made a valiant attempt, you got a lot of points already. You didn't get any feedback. You just got like a starter set of points. And because most people haven't completed it yet or anything like that. So you can still submit revisions, updates, more of it as we keep going through, and I will start looking and giving actual feedback, but you'll get more points. No one has a final score yet. That's just a bunch of points that you're getting as acknowledgement for having made an attempt already. If you haven't made an attempt already, then you haven't gotten any points yet. That's the point. But everybody's totally still can. Technically, it's not even due till this Wednesday, but we might even extend it past that. But now, here's the reason is there's a lot going on in homework 1. There's the answers, which I've been starting to give you already. I believe, all right, so let's be clear. I believe I've given you not only answers, but kind of adequate solutions through question 4 and 5. I think it's question 4 and 5. Or maybe it's questions 3 and 4. No, it is. It's question 4 and 5. I've given you solutions to everything I've said in class so far about question 4 and 5. If you were to put those solutions down, and as long as you honestly understand them and you're not writing anything that you don't honestly understand, then they would be sufficient for the full points. Now, why I take so long with homework 1 is there's a lot to unpack sort of behind these solutions. There's a lot of underlying math and deeper physics concepts that we will need to go forward in this course. Things that I gave you a surface view of question 4 and 5, enough so that you could do it and not feel confused or not feel frustrated. Now I want to circle back and start filling in some deeper levels of this, things that I think most of you have not seen in physics 1 or math class. So I hope it's not confusing. I mean, I'm going to go back. I'm not going to go to question 6 yet. I think question 6, 7, and 8, I believe it is. I think we've actually already said enough that you could probably answer those, most of you on your own. I think 9 is still we're not up to 9 yet. We won't be for a little while. But I think you could still do 6, 7, and 8 on your own. But I'm going to go back now and start unpacking the things that we used to do question 4 and 5 and expand on the mathematical details. So bear with me. So we're going back down the hole, kind of into deeper levels, layers, instead of moving forward of questions 4 and 5. What we're going to say for the next couple of days, I'm not saying you have to put all of this into your homework in order to get the points. That's why I've already given solutions and I'm already giving some points. But this is the reason that we assigned those questions, is it to springboard us into this material that you definitely do need for any exam or future material in this course. So So stop me at any point if that's confusing. So you're just going to take a bunch of notes now. We're going to say a bunch of things, and you don't have to think about the homework as such. Just think about the concepts. So, and please do take notes, obviously. So questions 4 and 5, they were all about work and energy conservation, right? And the way we set up this equation, 1f squared plus 1f kx squared equals 1f squared plus 1f kx squared, the way we set that up for question 4 and question 5, our GDP, our step 3, we said something like, we made an observation, a general principle that is always true. We said, when all the forces doing work on a system are conservative forces, then total mechanical energy is conserved for that system, by that system, from one location or one position to another. That's what we said. And then we said, or I said, okay, that's in general true. If you know, if you have some system, and here our system is a mass attached to the edge of a well-behaved spring. So when you have some system like a mass on a spring, and you know that all of the forces doing work on that mass are conservative, then you know no matter where the mass is, no matter what position it's in, it will have one amount of total mechanical energy, and that one amount will never change from place to place. And that's true, okay? I want to emphasize the place to place thing. I want to just emphasize again what we said 2 days ago, that this is a way of this statement, which I still have to unpack now. I mean, it's a true statement, but I'm not claiming that I've explained why it's true. I'm just saying that it is. I've just so far said that it is true. It's a helpful statement from a problem-solving point of view, because there's more than one type of conservation theorem in physics. There's more than one type of quantity that can ever be conserved. The one that we're the most concerned with in this class will be conservation of energy. And that often you're concerned with in chemistry as well and other science courses. There are other things that come up in physics, such as conservation of linear momentum or conservation of angular momentum. Or even if you're like on an atomic level, there's a such thing called conservation of spin angular momentum, etc. Even if you're not going on in physics, if you're going on in science and you ever have to take a standardized test like an MCAT or a GRE or something, if you ever have to take a test where they have a bunch of physics and they cover a bunch of different topics and they ask a bunch of different physics questions, what gets really hard for people, even if they sort of feel like they know their physics well, is they they often don't know which physics to use when, especially on these like smorgasbord broad tests. So one big hint I want to tell you or emphasize is, if you're ever given a problem where you know, and I said this Monday, but I want to say it again, if you're ever given a problem where you know, and please write this down, like it's not in my notes here, but I'm saying, if you're ever given a problem where you know the instantaneous speed over here at some position, like we do with our mass spring situation, like we know it's going 0 meters per second over here at 15 centimeters. And then we're asked, how fast is it going over here at 0 centimeters? If you ever find a problem like that, like in an MCAT or in a GRE, or et cetera, where you know the speed at one place and you need to know the speed at another place, a very good thing to consider is, oh, can I use energy conservation? Can I say that the total energy over here at this place is the same as the energy over here at this place? The reason energy is the way to solve problems like that is because other things, such as linear momentum, they are conserved, but they are conserved from one point in time to another point in time. It's a very subtle, but very enormous difference. And so if you ever see, so here, again, this is just like word to the wise, a kind of problem that comes up on MCATs, comes up on GREs, that comes up in fact, in criminalistics, if you're going on in criminalistics, in John Jay, a problem that can come up a lot is that you know the speed of a bunch of cars or two cars, the point in time before they crash, And then you know and you're being asked to solve for the speeds or the speeds of these cars after they crash. So you're given the instantaneous speed at one point in time prior to collision, and you're being asked to solve for another point in time. That's where you wouldn't use energy conservation. You would use momentum conservation. Energy is conserved from place to place. Linear momentum is conserved from time to time. That's just a good thing to write down or just to know for your future, for how to decide which kind of conservation to use for what kind of problem. All right, that's number one. Now, I still haven't explained why that is. That's what I want to get into over the next couple of days. But I want you to know that in this course, and definitely in this problem, we are far more concerned right now with energy being conserved from place to place. So I said, okay, when all the forces doing work on a system are conservative, we can use energy conservation. Okay, but that totally begs two big questions that I have to now start getting deep with. Oh, and I'm sorry. And I said, hey, this is an example. The only force doing work on the mass is the elastic Hooke's law spring force. There's only one force doing work on the mass. It is the Hooke's law force of elasticity exerted by a spring. And I said, and that force is conservative. So all the forces doing work are conservative. So we can say that energy is conserved. But what I never told, and that's all true, I'm not taking it back. It's not a lie. It's totally true. And it's totally valid to write in your homework. But it's not 100% valid to just write down because you may legitimately, like you should legitimately have questions like, wait a second. What does it mean for a force to do work? Did he ever tell us that? What does it mean to do work? And even more specifically, what does it mean to be a conservative force? How do I know if the spring force is a conservative force or not? Very good questions. That's what I want to back up now and start explaining in more detail. This is going to get us into some math that we need. In fact, to be honest, it's going to start getting us into some calculus that we totally need for this course. Whatever your calculus background is, we have to establish in a physics way for this course. So my goal now, I'm going to turn the page. My goal now is to start actually layering, like going down the layers of the math, the calculus that is required for understanding what work is and what a conservative force is. And this is going to take us a couple of days. Okay, so we're going to be on question 4 and 5. You already have the answers. You can turn it in. You can get the points. But I'm unpacking the energy, the work and energy ideas behind question 4 and 5 for the next couple of days. Please be advised. And also, again, that's why I'm not assigning any new homework for the next couple of days. And if that's not clear, please tell me in the chat. In the past, this sometimes used to confuse people how long I took. And the one difference I'm doing, how long I took on the first assignment. I'm doing it because the first assignment contains like a semester worth of important ideas behind it. That's why we signed it first. But just to be clear, again, in the past, I took so long on it by the time I even got to answers that people had no idea where I was. So hopefully it's a little clear to you that you have the answers now. Now I'm backing up. Okay, so you're just taking notes now that are inspired by homework 1B. All right, so I'm turning the page. Okay, so we're gonna back up and we're gonna unpack. Oh, and there goes I still agree with Douglas. I still think Douglas's suggestion is totally spot on, that I've got to be using this board. It's a good reminder to me to be more efficient. I've got to be using this board more, not to lose it. So I just lost it. Use it or lose it. Hold on. No, I really appreciate that Douglas pointed that out, and I really think he's right. But I'm still. Hold on. Where did it go? Hold on. Come on. Here it comes. And the delay is so funny too, because you think I'm lying, but you'll see it'll disappear on your side in a second. I think maybe I can beat it. Maybe I can beat the delay. Is that even possible? No, that would be like somehow violating Einstein's special theory of relativity or something. Okay, here it comes. Okay. Oh, maybe I am going to beat the delay. Wait, so weird. No, okay. Yeah, because how could that? All right, anyway, here, wait. Oh, yeah. Okay. Okay, so here's the board. Oh, I know why it happens in this class, because I'm not writing these out in live real time. I got to think about this. Yeah, okay, Douglas might have changed my life in a complicated but really good way. Okay, all right, so we're backing up, we're unpacking question 4 and 5. So what do we mean by work? That's the question here. And if you think you remember from a prior class, good, you can hold that in your mind. Anything you remember about work from a prior class will help you. But if you don't remember it at all, that's fine too. I am starting from scratch here. So you're welcome to look at this with a fresh slate, but hopefully no matter who you are, no matter, anyway, it doesn't matter. Okay, so what do we mean by a conservative force? That's our second question. So first, we're going to get into work, what I really mean by work in a calculus mathematical way. So let's introduce some notation. First of all, let Z, lowercase z, stand for some general measurable variable. I should even say independent variable. Let's assume Z is, well, some variable, quite often an independent variable. So Z could be X, Z could be Y, Z could be whatever. When we say delta Z, the lowercase delta, which is like the Greek equivalent of the letter D, what we mean when we say delta Z is a small but finite difference in two values of Z. Let's be very clear on that. I'll get into what I mean by small. I mean, that's a matter of context and perspective. But when we use the delta, when we talk about, for example, delta Y, like as in slope, as in delta Y over delta X, what do we mean by that? Like rise and run? Yes, but delta Y, we mean Y2 minus Y1, right? And when we say delta X, we mean X2 minus X1. We mean the difference, the actual subtraction of one value of the variable from another. So when we talk about delta Y and delta X in slope on a graph, we're usually assuming that we've got 2 points that are reasonably close to each other, and we're looking at the difference in their Y values and then dividing by the difference in their X values, right? So delta Z is what, but we assume that they are different, the 2 points. We assume that they are separated in a noticeable or measurable finite calculable way. So delta from now on in math and physics, if we say delta X, we mean probably a small, but definitely a finite measurable difference between two values of the X variable or whatever the variable is. So I'm saying Z just to mean variables in general. That's what delta means. Now let's turn the page and say, when we switch to D, there goes my board again. Okay, when we switch to the lowercase English letter D, we're saying the same concept. If we say dx or dy as in calculus, right? We're just saying, again, a difference between two values of a variable, such as x or such as y. Only now we're taking it to the limit. We're telling the world when we switch from delta x or delta z in this case to dz, we're taking delta z in the limit as it approaches 0. Now, so we're talking about now an infinitely small, or what you might call an arbitrarily small, like as small as you like, difference between two values of z, in this case, z. I want to really emphasize this because we are going to get into some real calculus here, like a lot more than we did in physics 1. I know it was technically required for physics 1, but you could sort of skate through physics 1 without really having to deal with it. I know that too. Calculus is a big deal in physics 2, and it is required for physics 2. Now, again, I'm going to be clear. I believe you've all taken enough to see it, to know what it's like supposed to be about, to have some practice and familiarity with it. I don't actually assume or even believe that most of you are comfortable with it. I don't assume most of you like calculus. I mean, if you do, I'm psyched, believe me. But I'm not assuming that you do. And I'm not assuming that you're totally comfortable with it. In fact, to almost risk insult here, I'm assuming that some of you who might even think you're comfortable with it because you do a lot of the procedures successfully and maybe got a good grade, I'm not even sure. You might even be more lacking it. I shouldn't say that. Some of you might even be kidding yourselves, even if you, I shouldn't even say that. The point is, I want to redo some calculus fundamentals here for everybody to make sure we actually know what the calculus fundamentals mean and where they came from in a context of physics. So what I'm saying right now is when you have a piece of notation like dx or dy, before anybody starts thinking derivative, before we get to a derivative, like dx or dy is not a derivative yet. It is a differential. Dx or dy just means An infinitely small difference between two values of that variable, okay? A differential is an infinitely small difference. And again, sidebar, a derivative, which I do assume, by the way, I do assume that people have some comfort with derivatives. We're going to redo them and stuff. It's really, it's integrals that we really have to get into here. And that's where I think there's probably some fuzziness, which is, and certainly some distaste, which is fine. But a derivative, remember, a derivative is like dy over dx. A derivative is a ratio of differentials. Right now, I'm just talking about a differential, an infinitely small difference from one coordinate to another. When you put one differential over another, when you take an infinitely small rise and you put it over an infinitely small run, then you have an infinitely small rate of change. And that's what you call a derivative. Okay, but that is a combination of differentials. A differential is an infinitely small difference. Now, before it involves the limit. Now, honestly, the limit is one of the key concepts of calculus. The limit is where we start actually dealing with infinitely large and infinitely small. We start dealing with the concept of infinity in a mathematically precise way. It gets very abstract very fast. Often it's the very limit that's actually where we lose people in calculus, some people, because it seems like a very fuzzy idea. Like when we say the limit as delta z approaches zero, we mean as delta z gets as close as you possibly like to zero without actually hitting zero. In other words, we mean when the two values of z get as close as you possibly want or possibly could imagine ever to each other without actually the two values becoming one value. Now that is what we mean. I mean, that is what we mean. But that sounds like a very strange, I mean, it's an exciting idea, but it might lose a lot of people. It might have lost you 2 years ago in math. For me, when I first heard that, to be honest, or when the first 100 times I heard about limits or being arbitrarily small or arbitrarily large, what kind of went through my mind, because I do like to use my mind. I like to think about crazy ideas. So I think in part of my mind like that, I was like, that's kind of interesting. That's wild. I'm sort of psyched that like people talk about weird things like infinitely small. But a big part of my mind was like, but this is math? Like that sounds very like I was like, I could almost talk about this in a philosophy class, maybe. That'd be cool. But like, how is this math if you're saying it's so close that it's as close as you want, but it's not close enough to be nothing, or it's not close enough to be there? I was like, that does not sound like what I signed up for in a math class. I thought math was supposed to be precise and black and white. Well, first of all, I was wrong about that, but it didn't seem very satisfying. And then even worse, to hear about that in a science class, to think that derivatives or limits have anything to do with the world of reality, of observable, experimental, reproducible, measurable, quantifiable realities. How the heck in reality, in science, is it meaningful at all to say the 2 points are so close that they're as close as you like, but they're not close enough to be on top of each other? Like the difference is as close to zero as it possibly could be, but it's not zero. I don't know what your brain does with that. My brain kind of sometimes just accepted it as like, all right, this is another one of those pieces of nonsense. I'm just going to do it and get it right on the test. And sometimes my brain just rejects it. It's like, I do not get this. I do not like this. I don't know what you're asking me. I can't do this test. I want to say here and now, so it took me years and years to work through in my mind, and maybe you're way ahead of me on this. It actually is shockingly scientific. Actually, science, physics, the lab is the place where, to me now, the idea of infinitely small makes the most sense. As it says on the sheet, so I want to take a pause to tell you, when we ever say from now on in a physics class, a differential, when we say that two values are infinitely close to each other or arbitrarily close to each other or as close to each other as they could be in the limit as they approach zero, here's what we mean. What we mean is, well, it says it right here. A difference that is infinitesimal, a differential, is one that is large enough to affect measurements in the experiment, measurements made in the lab, but not large enough to be quantified on a measuring device. In other words, infinitesimals means they affect measurements. They're there in an experiment, but they're not measurable. They're too small for our measuring equipment. They're between the cracks of our measuring equipment. That's what infinitely small means from our perspective in our context. So very literally, as an example, let's say you're doing an experiment with mosquitoes, or maybe even electrons, but let's say mosquitoes, okay? And there's mosquitoes buzzing around, and you got this one mosquito, and you know the mosquito's buzzing around and affecting the velocity of other mosquitoes, or it's buzzing around and you can almost measure its velocity or its energy or something like that, right? But the meters, so it's there. It's not zero, the mosquito. The length of the mosquito is not zero because there it is. It exists. It's being observed in the experiment, and it's affecting the experiment. But you've got this meter stick that's divided into meters and then divided into smaller line gaps called centimeters, or maybe it's even divided into millimeters. But if you were to put this meter stick next to the mosquito is between the cracks of the meter stick. And so it's there, but you can't put a number to how big it is. So its length is non-zero, but its length is below the threshold of measurement. So that for us means it's infinitely small. It's as close as it could get to zero. And here's the point. Could it be even smaller? Like, why am I saying that's as close as could possibly be to zero? Why am I so audaciously saying that means it's infinitely small? I'm saying it because even if that mosquito were smaller, I couldn't put a number to how much smaller it just got. Any two mosquitoes that are below the threshold of measurement, even if they're different sizes, I can't detect the difference in their size. So they both have size, but they're in a category of size that's below numbers. That category is called infinitely small. It's okay. It means immeasurable, below the threshold of measurement. So I'm just saying that as a way to picture. So if you want to, so from now on, if I ever say something is arbitrarily small or infinitely small, it's not like Harry Potter. It's not black magic. It's not a weird thing. It's a category. It means below a certain threshold, but above another threshold. And we're using a word like infinitely because what we're saying is it exists in the world of quantification, but we can't quantify it. Okay. So that's what an infinitesimal is. So dy, as in dy over dx, dy just means an infinitely large rise in the y coordinate from one y coordinate to another on a graph. Dx means infinitely small run from one x coordinate to another on a graph. Okay, so now I'm going to give you one more piece of notation. Now this next one we're not going to use for a little while, but we're definitely going to use in this class. So I just want to put this as a package. So the next piece of notation is if you ever see. And I'm about to lose my board again because I talk too much. Yep, hold on. This is like probably the best training course for my efficiency. And you notice too, I put more things in while I'm getting this. In the Google class, there's more game portals where you get points if you either tell me to slow down or you tell me to speed up. I mean, look, and again, for what it's worth. But anyway, and I'm sure what I need here is to speed up. But okay, here comes this next piece of notation. Boom. If you see something that looks like a backward 6, so it's like a contorted D. You might think of it as a lowercase delta, but it's not actually. It's some Celtic symbol or something. We read that as partial Z. And that's another kind of infinitesimal that we're going to need in this course. It also means an infinitely small difference between two values of Z. But we use that symbol. We call it the partial Z. It's called the partial differential of Z. We use that symbol whenever the kind of infinitesimal we're looking at is not the whole picture. That is, whenever we have some function we're looking at where Z is one of a number of independent variables, where some factor depends on Z, but also depends on other things. If and when Z is not the only independent variable, then we use this symbol to remind ourselves of that. This comes up, in other words, when we have functions of more than one variable. Technically, that's called multivariable calculus. And in this class, we do have to do some of that together for the first time for many of us. But when that comes up, when we have soon, when multivariate functions come up, we use this symbol to connote a partial differential or a partial rate of change. Okay, just put that in your bank for now, just notate. So we have three pieces of notation now. Delta Z means small but finite difference, or delta any variable. Delta X means small but finite difference in X. Delta Y means small but finite difference in Y. Then DX means infinitely small difference in two values of X. And then partial X means infinitely small difference in two values of X when X is not the only independent variable being used. Okay, now, given that notation, that's a bit of calculus notation, which we're going to come back to. But just laying that foundation down, or laying that notation down, I'm not going to use it. I'm going to turn the page and I'm going to shift gears a little bit. Now I want to talk about vectors. Okay, that was a little bit of calculus. There's going to be more. I'm going to shift gears and talk a little about some vector stuff that we need for doing this physics. So let's go back to some physics. Let's define, let F, the vector, be some force vector, i.e. some magnitude of newtons pointing in a certain direction. And let delta X be some small but finite displacement vector. So we've got some small but finite difference in two positions, X1 and X2. So that's a display in some direction. We got some displacement vector, delta X. And let's say that we apply a force vector of F to this displacement delta X, then what we're going to, and well, let me show you, like as in an example, I'm going to turn back the page in a second. But for example, let's say we've got this mass on the floor, this box on the floor, and we push down on the box with a force vector of 20 newtons. Like we push, the magnitude is 20 newtons and it's in some direction, like down and to the right. And let's say that we succeed because we push this box, we succeed in pushing the box forward along like a horizontal floor. So we don't push horizontally. We push down at the box at some angle, and we succeed in pushing the box across the floor some number of purely horizontal meters. So we've got a force of 20 newtons at some direction, and we've got a displacement, I should say. And we've got a displacement of purely horizontal of 5 meters. That's our example. Well, first of all, I'm going to say, as a definition, if you've got a force vector acting throughout a small but finite displacement vector, then you multiply the two vectors together and you get the small amount of work that is being, the small but finite amount of work that is being done for that small but finite displacement. So my definition I'm giving you is delta W, small but finite amount of work, is defined to be the scalar is a scalar. Notice there's no vector symbol over my W. That is not a typo. That's actually super important. Delta W, the small but finite amount, like amount, pure magnitude, amount of work that is done throughout this operation is a product of the force vector with the small but finite displacement vector. That's a definition. Now I'm going to unpack that, but I'm saying it as a definition that would apply to a case like this one where you've got this force vector and this displacement vector. Now, first of all, to relate this back to what I was saying before, I keep saying over. So I'm defining here, I'm not defining work. I'm defining work in a small but finite case. You're going to see, and by the way, that's all I'm going to be talking about for the rest of this period is work in this small but finite case. By the time we come to class in 2 days, that's where I'm going to expand this and show you how we expand the idea of work for a small but finite case into a larger case of work that doesn't have to be so small. Today's all about small but finite. So the first question you might well ask, I mean, it would be very reasonable for you to be thinking or saying is, hang on, I keep saying small but finite. What the heck do I mean by small? I mean, especially in this case, like I said there's a force of 20 newtons and the thing is being displaced 5 meters. 5 meters does not sound small, or it doesn't to me. Or like, what small compared to what? Why does the average keep saying small? Hopefully 5 does sound finite to you. I mean, 5 is finite. It's a number. It's measurable. It's not infinite. But why do I keep calling it small? What is small about it? Good question. What I mean by, and small depends on context. It depends on perspective. But as a scientist, what I specifically mean by small is I mean that the 5 is small enough that the F held steady. What I mean is I'm pushing this box across the floor and I'm pushing it like with my arm. If I had gone far enough, if I had pushed 5 meters might be very large compared to some contexts. But what I'm saying is if 5 is not too large to get me tired, if the 5 is not too large to yield a situation where my F starts shrinking in magnitude because I'm getting tired, or if the 5 is not large enough that for whatever reason, the 5 is short enough, quick enough, small enough that I'm able to hold F at a constant value of 20 for that entire thing and keep my direction. Also, 5 isn't large enough to start causing me to rotate the angle of my force. That force vector held steady for the entire 5. That's what I mean by 5 being small. As long as it's small enough to allow us to plug in one constant F value, then that's what we mean by small, okay? So when those cases, in other words, I'm saying so far, as long as delta X is small enough that you only have one F value, then there's not a lot of complexity. In order to calculate work, the work done by that force, you merely multiply, well, almost merely multiply the force vector by the displacement vector. And the product of the two is what we mean by work. It's a definition. What we're trying to say is, look, force is something that happens at a point in space and at a point in time. I push or I pull something instantaneously. But if I ever wanted to look at the accumulated consequence, the accumulated effect or impact of my force over some finite measurable region of space, if I want to see what my force is accomplishing through space from one point in space to another, if I were to multiply the magnitude of my force by the magnitude of the displacement that it accomplished, that would presumably be a pretty important thing to keep track of. We're going to call that work. And the whole idea of it being a multiplication is we're saying if you're not pushing or pulling something at all, you're not doing any work. But also if you are pushing or pulling something, but you're not accomplishing anything, if you're not moving the thing, then you might be pushing or pulling it, but we already have a word for that. That's called force. You're not accomplishing anything throughout space. If you push or pull something such that it actually changes its position in space, then you've accomplished something. Ultimately, we're going to say you've transferred energy to it. So we call that whole product work. It's a multiplication, because if either number gets bigger, then the whole package gets bigger. And if either number is 0, then the whole package is 0. So that's the operation that multiplication captures. And we ultimately want to say that this work that you're doing when you push something through a distance is a scalar quantity. Because we're ultimately going to say it represents how much energy you transfer to the object, and you either did transfer a certain amount of energy or you didn't. But you don't. Just like temperature could be a positive number or a negative number or a big number or a small number, but no one ever says it's 30 degrees Celsius to the east. Like temperature isn't a vector. It doesn't go in a particular direction. Same thing with work, or same thing with transfer of energy. It's just an amount of accomplishment in space. It itself does not have a direction. So what I'm saying so far is that if you multiply one constant force vector by a small but finite displacement vector, if you multiply the two numbers in a certain kind of way, if you multiply the two vectors, you get a number which we call work and is measured in newtons times meters, which we call joules. All this is fine, and I think, and we could go on to bigger and better things, except for one thing. So the first question was, what do we mean by small? Hopefully I've answered that. But the second question is, hang on a second. How is it that, I'm just going to draw on this so I don't lose my board. Hi, Doug. Okay, just kidding. The second question is, wait a minute. How is it that we're multiplying two vectors? Yeah, each is a magnitude, and a direction, two arrows. We're apparently multiplying two arrows together to produce or to yield a value that doesn't have any direction, a pure scalar value, a pure magnitude. That is what we're doing. We're saying force vector times displacement vector equals work, the scalar. Like, yeah, work is a scalar, it says in the top right. Okay, this gets us into some vector mathematics now, which again, I'm teaching you right now. If you have heard any of what I'm about to say about scalar products of vectors, that's great. I don't think I'm going to contradict anything you know. I think any background that some of you might have will only help you feel comfortable here. But to all of the rest of you, I'm saying I don't expect that you've heard this before. I'm not assuming you've heard it before. I'm telling you now that when it comes to, so we're into a little vector math here. When it comes to multiplication in the land of vectors, there's actually three different ways that vectors can be subjected to multiplication. There are three different ways, and you might want to write this down like in your notes because it's not written right here on this screen. I'm saying you got, whenever multiplication is taking place in a context of vectors, there's three different things that could be happening. One, please write this down again. And by the way, this would be another thing if you write this down and you screenshot and you send it for participation, like, that'd be great. I'd be really happy. One, a vector could be multiplied by a scalar. That's legal. Like, you could take a force vector and say, oh, I'm now pushing twice as hard. So you multiply the force vector by the number 2. You say, I'm pushing twice as hard. And when you do that, what you'd be saying is, I just increased the magnitude of my vector by a factor of 2, but I'm still pushing. Presumably I didn't change anything else. I'm still pushing in whatever direction I was ever pushing in. So in effect, when you multiply a vector by a scalar, you take an arrow and you scale up the arrow by a certain amount, or you scale down the arrow by a certain amount, but you still end up having an arrow. In other words, what I'm saying is, whenever you multiply a vector by a scalar, always what you get is a vector. That is statement number 1. Please put it in your notes. I'm saying multiplication of a vector by a scalar always produces a vector. That is not what's happening here, but that's a thing to know. Choice number 2 is, you could have two vectors. You can have two vectors and multiply two vectors together. When you do that, there's two different ways of doing it. One way is you can choose to use an operation called a scalar product, or more commonly a dot product. You'll see on the next page in one moment. When you're facing two vectors, you can choose to multiply mathematically. You can choose to do a mathematical procedure which multiplies the two vectors together in such a way as to produce a scalar result. Technically, that's called the scalar product of those two vectors, or what we commonly call it, a dot product, because we use a dot to denote it, as you saw 3 pages ago. So that's choice number 2. Choice number 1 is multiplication of a vector by a scalar. It's not really a choice, like you just do it when you see it. But if you have two vectors, a choice is you can multiply two vectors according to what's called the dot product, and you will therefore find a scalar answer. Or choice number 3, the other choice is, if you're facing two vectors, you can choose to multiply the two vectors by a procedure known as the vector product, or more commonly the cross product, because there, instead of using a dot to connote multiplication, we use the X, like from 2nd grade. Now, this is a choice. I'm going to I will turn the page. I'm saying here in this context, I'm going to talk about this page. In this context of work, the physics context of work, we are faced with two vectors, a force vector and a displacement vector. We want to see what the scalar product of these two vectors is. So we choose to deploy what's known as a scalar product. I want to emphasize strongly, before I go further, that like so much of physics, this is a choice. Any two vectors you ever meet walking through the forest, could be multiplied by a dot product or could be multiplied by a cross product always, and they'll just yield two totally different types of answers. And which one you choose to do is just that. It's which procedure you choose to use based on the physical context and the type of thing you're trying to solve. Just like if you ever face two numbers, 2 and 3, you can choose to add them together and get 5, or you can choose to multiply them together and get 6, or you can choose to divide them or subtract them. Depends on what like the word problem is that motivated you to look at these numbers, right? So, okay, so vectors can be multiplied together by a dot product or by a cross product. Today, I'm going to explain the dot product. I'm not going to explain, you might guess where I'm going to be going with the cross product. On another day, when it becomes physically appropriate, I'm going to explain how the cross product works. But today, when we are trying to figure out the work done by a force throughout some given displacement, what we're looking for is some kind of multiplication of those two quantities that itself does not have direction. So what we choose to do is a dot product. Okay, so here's how the dot product works. Well, the definition of it is right here in the middle. If you were given two vectors, two arbitrary vectors, vector A that has some length in some direction, and then some other vector B that has some length in some direction. You could draw them anywhere you want on the page. So you could draw them right next to each other, tail to tail, and look at the angle, the acute, most straightforward angle between their two directions, right? And when I'm saying, as a definition, but then I'm going to explain it, is if you want the dot product of these two vectors, what you do is you multiply the length of one vector times the length of the other vector, and then you multiply that by the cosine of the angle between them, between their tails, the acute angle between their tails. Specifically the cosine. It's like not an example, it's like the rule. Notice that, first of all, notice if you multiply the length of one times the length of the other, the length of one is a number, the length of the other is a number, and cosine of an angle is always some number. It's always some fraction, right? Between like -1 and 1. So you will get a number. That number you get is the scalar product of these two arbitrary vectors, A and B. Now, let me explain why this rule is this rule and what it has to do with work and everything. The reason that the dot product involves this cosine term. So first of all, let me back up again and remind you, cosine is always a fraction. Or you can even think of it as like a percentage, right? Cosine it could be 1/2. It could be, it could be like 0.50, like the cosine of 60 degrees, or it could be like 0.866, like the cosine of 30 degrees, or it could be 0.707, like the cosine of 45 degrees, whatever. It's always some decimal that you could think of almost as a percentage. What this definition is saying is if you want the scalar product between two vectors, first is you're asking really like what's the product of their two lengths, but then you're sort of scaling down your answer by a certain percentage or certain factor, and the factor comes from the cosine. What that factor is doing is really registering or measuring or incorporating the extent to which these two vectors do actually share a direction. The cosine is multiplying your whole answer by a factor that indicates or registers how parallel or aligned these two vectors are. What you're doing is you're asking for a result that does not take into account direction. So in effect, what you're really doing is you're saying, I'd like to look at how long each one of these vectors is, but I kind of only want to look, I don't want to fully multiply by the length of each one. I want to really multiply by the amount of length of each one that's like lined up with the other. I want to almost treat these two vectors as much as I can as though they were both lying along the same number line. And then, like before I just do regular number line multiplication of numbers, I kind of want to think of to what extent these two vectors are lined up in the same axis as though they were just two numbers on a number line. Cosine does that for us. Why? Like, why does Well, the real simple answer for those of you who are following me, the fast answer is sine super, cosine crappy. Or put another way, remember, if you're ever going, I mean, I love the unit circle. I love the unit circle. I mean, I just sit around. I mean, I just love the unit circle. Some of you do, some of you don't. But even if you find the whole unit circle thing intimidating and all the values and stuff, if you're going to hang your hat on any one basic thing from trigonometry, always remember that that sine super, cosine crappy, or cosine counterintuitive, meaning this: the sine of I should even ask. Wait, do I have time to ask you guys? We've got 20 minutes. Let's just do this quickly in the chat or somehow. You can do it privately or publicly. What's the sine of 0? You can get points for participation in this. Oh, everybody wake up. That was fast, Alex. Thank you. And I didn't mean it for him to be him or to be a race. Other people could do, and other people are doing it. Great. It's not a race. If you do it, you get total karmic credit and love and peace and understanding. And some of you are private, some of that's fine. And I shouldn't have said whether he was right or wrong, but he is totally right. And that's awesome. If you know that, and good. Thank you, Alex. Thank you, Amanda. Thank you, Caroline. Thank you, Caitlin. Thank you, Steve. Thank you, people. Thank you, steel type Pokemon and water type Pokemon and grass type Pokemon. Thank you, Evan. Thank you, Estrella. Thank you, Erica. It totally is 0. And that's a good memorizer. The sine of 0 is 0. And here's why I say sine is super. The sine of 0 is 0, which is just as you would almost hope if you were a snake. And then as the angle gets bigger and big. Oh, okay, cool. Thank you. Okay. So thank you, Stephen. Well done. Awesome. And that I think you could submit that kind of like 400 different portals of class participation, by the way. But okay, like the sine of 0 is 0. And then as the angle gets bigger, the sine gets bigger. It's super that way. It's like exactly like logical what you'd make up if you were forced to on a desert island, if you were making up functions. As the angle gets bigger, the sine gets bigger. And when the angle is nothing, the sine is nothing. Now, cosine is the opposite, right? Like I always remember sine 0, 0. The sine is super. Cosine is counterintuitive or crazy or crappy or whatever. Cosine, when the angle is, well, I think what's the cosine of 0? Anyone? What's the cosine of 0? This is harder actually, but it's easy. If you know that good. That's actually a really good answer. And you, Alex, should submit that. There's like at least 4 portals of points that would apply to. If you think about, I know why you said that. That was a great answer, and it was fast. And I know that you're paying attention. You're thinking of what angle makes a cosine of 0, which is 90. In effect, you just did the arc cosine of 0, which is awesome. And you've got the right, but yeah, it's like backward, right? The point, I agree with. So please submit that, and not to. I just want everybody to understand. Remember, Alex can submit that for 1 million portals, even including one, and I'm saying this with complete respect, even one where he gets credit for an answer that's not correct, right? Because it takes so much guts, and it shows that and plus I know what he was thinking, and I'm sorry. Also, I'm saying Alex, hold on a second. Hold on. I mean, I know it is Alex, but Alex, hold on. Wait, I have to also apologize because since Alex is a Black, I'm sorry, I don't honestly know whether it's he, she, they, or because of the name out, but who, and you could tell me privately or whatever, and only because I just don't know you yet, but anyway, Alex, and I don't want to make a big deal of this, but I kind of do, because Alex is like, I know exactly what Alex is thinking, and clearly Alex is thinking, and there's portals that apply and get points for that, and even one of them nobody else could even get right now, because one of them is for the fact that the answer is not exactly correct, which I'm trying to make a good point of, not like a shaming point of, and I hope that's clear. Now, indeed, and if anything I'm saying is not clear, or you don't know what portal I'm talking about, you don't know how to get the points, definitely ask me in direct chat. Okay. Oh, I'm so right. And I should have known that. Oh my God. Okay, well then that means there's 400. Okay. Sorry, no, this is good. I mean, this is good. That's very clarifying. Also, I'm glad you might have to remind me of this 1 million times too when I go to do the grades and okay, fine. And I hope you know what portal I'm talking about and all of that. And I hope you understand this is all with respect and admiration, not the reverse. But okay, so back, and I will remember. Back to everybody with the math. Here's the deal. And also I am watching the time and we are almost there. But sine is like the straightforward one, but cosine is kind of funky because it's the opposite. The cosine of 0 is 1. And then as the angle gets bigger and bigger and bigger, the value of the cosine goes down until all the way when we're at 90 degrees, when we're at perpendicular angle, then the cosine is 0. Now that's like really bizarre in a way when you first, but first of all, in order to remember it, just remember it's the opposite of sine. Sine is the straightforward one. Sine is straightforward. Sine is super. Sine of 0 is 0. It's like you're speaking like a snake or whatever they call that in Harry Potter that I forget, whatever that snake language is. And if you put it in the chat, you'll get points for that. But cosine is the opposite. Now, or you could say cosine is confusing. But now here's the first time in my life where I started to see what the value of the cosine is. Here's the value. Here's the value. Is like, look, let's back up. And again, I know this is all mathematically abstract. It's hard to know where the physics is here. Yeah, you will come back to physics, but just bear with me. If you look at just some random vector A, right? Think about physics 203 and physics 1 now. You just draw some random vector A that's up at some angle. Yes, I knew someone would do that. Parcel tongue. Thank you, direct chat person. That's awesome. Yes, parcel tongue. You did. Oh, 2 people in the private chat. I shouldn't have just said it, but that's awesome. You totally get points for that. Totally, just because, again, just if nothing else, because you're paying attention and being a human being. That's awesome. And also, I need that to remember that to talk to my son. Thank you. Right. That's awesome. Okay. You have this vector A that's pointing like this. It's at some angle from the coordinate axis, from the x-axis theta, right? Remember from physics 1, when we wanted to add this vector to some other vector or something, like it was a displacement vector, and we wanted to add it to some other displacement vector to get the total displacement, we had to break the vector into components lying along the constituent axes, right? So we would break up the vector A, we would use SOHCAHTOA. We would say like, okay, vector A is actually the hypotenuse of some right triangle. It has 2 perpendicular legs. How do we know it necessarily is part of a triangle that has 2 perpendicular legs? Because there's 2 legs necessarily that point along the 2 perpendicular axes of space, the x-axis and the y-axis, right? So we would break up our vector into an x component or an x leg, if you like, and a y component or y piece in effect. And we would say the length of the x component of A, of vector A, the length of the x component, the length of that horizontal side, that horizontal leg, that side that's adjacent to the angle, we would do SOHCAHTOA. We would say cosine of the angle equals adjacent over hypotenuse. Therefore, adjacent equals hypotenuse times cosine. So we would say that adjacent leg down there, the length of the horizontal component of A is A times cosine of the angle, right? And the other component, the vertical component, would be A times sine of theta. Now, what did A cosine theta really mean? And notice, the smaller angle theta is, the more that hypotenuse falls down towards the base, the longer, the more it would be just like the base. In other words, A cosine theta is some percentage. It's some portion, some smaller, the length of A cosine theta is some fraction of the total length of the hypotenuse. The smaller that angle is, the bigger the fraction. If that angle goes all the way down to 0, A cosine theta and A are the same bloody thing. Bloody Harry Potter. But if A were all the way up here, then there'd be no component of that on the x-axis, right? It'd be 0. What is that length? So that length, A cosine theta, is some percentage, some fraction of A that gets bigger and bigger, bigger and bigger as A drops down and gets more and more parallel to that axis, right? Very specifically, what you could say is that A cosine theta, the x component of A, what it is, many people call it a projection of A onto the x-axis. It's as though you took a light, so as though A were like some arrow sticking out of the ground at some angle, and you shined a light down onto that arrow, the light would cast a shadow on the ground. from the arrow. And the length of that shadow is what we're talking about here when we say A cosine theta. Now, it's also true that if you shine the light over here, then the shadow cast on the wall is what we mean by A sine theta. But I want to focus on that A cosine theta thing for a second, because what I'm saying now is if you put one of the vectors on an axis and then put our other vector, so you take our two vectors, A and B, or ultimately in physics, you take our two vectors, force vector and displacement vector, and you put them together. When we say AB cosine theta, what we're really in effect saying is A cosine theta times B. We're saying the projection, the portion of A that's lined up with B times B. We're not really multiplying both lengths together. We're taking the portion of one of the vector's lengths that would lie along the other, like the shadow that would be cast by one, the length of that shadow multiplied by the other vector. Or if you like, I mean, multiplication is commutative. You could think of it as one full vector times the projection of the other one onto it. AB cosine theta means the same thing as A cosine theta times B, or A times B cosine theta. We are multiplying. What we're doing when we throw in that cosine theta term, we're making sure that we ask ourselves, what would these vectors look like if they actually were lined up? If we only look at the aspects of the two vectors that are actually interacting with each other on the same axis, we multiply those. That is what we mean by, and so then we get a number just on the number line, because we've gotten rid of the directionality by doing this. So the dot product of any two vectors is the length of one vector times the length of the other vector times the cosine of the angle between them. If the two vectors are already purely parallel, then you're going to multiply the one length by the other length times the number one, and you're just going to get the full answer. Like if they're already on the same number line, if they're perpendicular, because the cosine of 0 is 1. If they're perpendicular, you're going to take the full length of one, and I don't care how big it is, you're going to multiply by the full length of the other one. It might be super big, but if they're perpendicular, the cosine, and this goes back now to Doug, like if the angle, but if they're purely perpendicular, the angle between them is 90 degrees, you're going to multiply that whole thing by 0. You're going to say there's no dot product at all. So this is the dot product. It's the measurement of two vectors to the extent that they are lined up, to the extent that they share a direction. It is therefore the non-directional product of them. What does this have to do with physics, or why do we use this in physics? Because now what we're saying is, look, well, actually, let's go back to the physical example I gave here. If we have this example where we've got a force vector and a small but finite displacement vector, what we're really saying in physics is like, I'm pushing this thing and it's going somewhere, and I want to multiply the two numbers together to see the overall impact, the overall accumulated consequence of my push through space. But I'm pushing at an angle. Only the horizontal component of my push is affecting or interacting with or relevant to the horizontal displacement of this mass. So I don't really want to multiply 20 by 100. I want to multiply 20 cosine 60. I'm sorry, I don't want to multiply 20 by 5 and get 100. I want to multiply really 20 cosine 60 by 5. Or if you like, 20 times 5 times cosine 60. I want to dot these two vectors together to find out how much of my force, how much of the relevant piece of my force is actually producing this displacement. If I push down on the box, or gravity is pulling down on this box while the box is displacing along the floor. Gravity is, I mean, the box has a weight on it, mg. Gravity might be really heavy, but the amount that gravity is pulling down on the box has nothing to do with how far the box is displacing horizontally. So the dot product, we want work to capture that idea. So the dot product between this and this would be 0. Gravity is not doing any work on the box. So I'm just saying, we're almost done. So I'm saying the definition here, the definition of work is a scalar that is a force vector dotted. Like that is literally a dot right there. It's not just like random multiplication. It's the dot product of the force vector with the displacement vector which really means then, and to do this example, to finish this example, if we want to know the work done in this example, it would be the force vector dotted with the displacement vector, which means the force magnitude times the displacement magnitude times the cosine of the angle between them. So it's 100 newtons times 5 meters. Those are numbers, times the cosine of 60. And the cosine of 60 is 1/2. I should have written that down, but it is. Well, yeah, 1/2. So we get not 500 joules, but 250 joules. I'm assuming that a joule is a newton of force times a joule of work is a newton of force times a meter of force. So in this case, so the dot product of these two quantities would be 250 joules. Ultimately, what I'm saying so far is for a small amount of displacement, to calculate a small amount of work, you do the dot product, the scalar product of force vector with displacement vector. You do force magnitude times displacement magnitude times the cosine of the angle between them. We have 4 more minutes. I want to do one. We're almost where we need to be today. I'm happy. But one more sidebar just to keep the math and the physics going in step. Is it ever meaningful in physics to multiply a force vector times a displacement vector and get, can you ever vector multiply? Can you ever multiply a force vector with a displacement vector and get a vector? Yes, you can. And when you do, you can do something called a cross product, which we'll learn next or soon. You can choose to do that. You just don't get this scalar quantity called work. You get a whole different thing, a vector quantity that's called torque. When you look at a force vector and multiply it by a displacement vector in a manner that preserves their direction and takes into account not their parallelism, but their perpendicularity, called torque. Just so it's a choice of which one you do. When the math behind calculating the physics of work is doing a dot product. Now, someone's here for the last 3 minutes. Okay, we have 3 minutes. Where am I going? I have a way to go with all this. This is still just calculating work. This is all in theory background for questions 4 and 5. Again, you already gotten the answers, but I'm just trying to build up some things here. This is for calculating work over a small amount of displacement, small enough that the force does not change. What if? We're going to do this very quickly. So question 3. If you start pushing this box, or some force starts pushing something, such as a spring, starts pushing a block over a large enough distance that the force starts varying, so that you have some force that's relevant over here at this position, and then a different force that's relevant over here at this position, and I've got 2 minutes left, then that's a different issue. That's a harder issue that we have to spend most of Wednesday talking about. But the first answer to what we do then, when delta X starts becoming large, the first thing we do then is we adopt the principle of superposition, which says that the whole is equal to the sum of its parts. It's actually not obvious. It's not even always true, but it is true here. We believe that the whole amount of work that you do over lots and lots of little displacements would equal the sum of all the little works you do over those little displacements. In other words, and this is where we're pretty much going to leave off for today, work over a large displacement, so no delta, I've got no delta here, what work will equal the sum of lots of little works. In other words, will equal the sum, this means sum, right? In short, what I'm saying is, if you have a bunch of different, if you have displacement is large enough that you have a bunch of different Fs for each one of the little displacements, then what you do, so say right here, I'm pushing in my force is 100 newtons, but then I, over here in the next 5 meters, the force is 200 meters. And then over here, for the next 5 meters, the force is 300 meters. What if it's that straightforward where it's like changing in chunks like that? I hope it doesn't seem too illogical to say, well, what I could do is just calculate the work over here. I could do this force. I could set my counter at 1 and say, okay, I'm going to do the first force and the first displacement. Sorry, what just happened? What just happened? Oh, okay. I know we're just about done. Hold, and this is my last statement. We just don't need to. So I would go over here to this first little displacement, multiply the force by that, multiply them together, dot product them together, put them in my bag, then walk to the next 5 meters, multiply it by the new force, multiply them together with dot product, put that in my bag, walk to the next, and just add them all up, and that will be the total work. The only question is, well, actually, I'll just leave it at that for the moment. That's it. It's 420. We'll pick up on that and turn that into, we're going to turn that into an integral on Wednesday. That's where this whole thing is heading. We're going to turn that delta x into a dx and turn the whole dot product into an integral. That's where it's, but yes, have a good day. Thank you. Sorry. Have a great day. Thank you. I'll hang out if there's any questions, but other than that, yes.
Bye, have a good day.
You too. Thank you. Have a great day. I'm changing.
Bye, Professor. Thank you.
Thank you very much. Have a great day. Awesome. Thank you. Okay. Thank you. Have a good day. Yes. Have a nice evening. Gotcha. Thank you. Okay. Awesome. Sumaya, Adan, you guys are cool. Are you copying this down? Do you have a question? Are you good? You there? Going once, goes away. Adan, Sumaya, are you there? I'm cool. Oh, okay, cool. Oh, okay, cool. Take your time. Great. No, fine. Don't rush. I just want to make sure. Thank you. That's why I should really put a portal in for that. Actually, I think I sort of did, but cool. Okay, cool. Thank you. Have a good day. Okay. Okay, well, this has been a production of productions. We thank you very much, and we will see you. We will see you next class for integrals as sums taken to the limit.